Hello, my name is William Ahern, and this is my final project for EGR214, Numerical Methods for Engineers, for the semester of Fall 2024, with instructor Dr. Hans Chapman. The final project is the use and evaluation of cross products and position vectors with MATLAB and Python. Our related course is EGR220, Engineering Statics, and this project will include illustrations from Engineering Statics by Russell C. Hibbler. The analytical approach to cross products is to say the mathematical approach, is to create a 3x3 matrix and solve it using the determinant method. The determinant method is to cross out your row and your column of your component and then to cross multiply the remaining pieces. So in this case, we have our I component, and what we'll do is we'll cross out our I row and our I column, and then we cross multiply RY, FC, and then we subtract RZ and FY. And then we'll subtract our J component, but do the same thing interior of that, and then add our K component and do the same thing interior of that. And cross products are really useful for creating orthogonal vectors. So our resultant vector, the moment about point O, is going to be orthogonal, that is right to, in direct perpendicularity to, R and F. And that helps us determine moments. Problem for this project, our cross problem, is determine the moment produced by the force F in the figure about point O. So old MacDonald here is on his tractor pulling the tree down, and he's going to pull it down about point O, the base of the tree, or the origin of our coordinate axes. And we're supposed to express the result as a Cartesian vector. Now analytically what we do is we start by converting all forces and positions to Cartesian coordinates. So our position, RA, or R really, would be 4i plus 12j plus 12k, and that's our position vector. Next, with our forces, what we have to do is actually have to make a unit vector, so we'll take the total magnitude of our force, which is 2 kilonewtons, and we'll multiply it by the unit vector of position, which is the force, or the position vector, right, that we determined earlier, and then divide it by the magnitude of our position, and that gives us this beautiful force vector. And then we'll cross that force vector with our position, either one. RA is used simply because it has 2 zeros in it, which makes math easy. And then we get our determinant, which is negative 16.5i x plus 5.51j y in kilonewton meters. And that's our analytical answer, so we need all of our numerical answers to align with that. In MATLAB, what we'll do is we'll take inputs from the user for each component of our vectors. So our position vector in meters will be A1, A2, and A3, and we'll ask the user for each component, the I, J, and the K component, and then we'll create an array from that, and that array can then be used as our position vector. The same thing will go for our vector B, which is our force vector, and we'll get the force vector I, J, and K. And then what we'll have MATLAB do, because MATLAB stands for Matrix Laboratory, so it's really good at this sort of stuff, is to cross those two products. We don't have to do any math. We just tell it what we want it to do, and it'll do it, and it'll spit out what we want, which is our cross product, right, which is equal to the cross of A and B, and then we'll spit out our units, and that gives us negative 16.5 and 5.51 in kilonewton meters, and that is the correct answer. A very similar approach can be taken in Python, where we have our vector A, but we have to import our module as NumPy to properly do all this. And we'll create an array, but instead of having an array with 3 variables and then taking inputs for the variables, we'll just use the input as the variable. So instead of saying A1 equals input, you just say that the first component of our array is the input, and then the second component and the third component. So I, J, and K are equal to inputs. Vector B, I, J, and K equal to inputs, and then we tell it to cross in a very similar manner to what we did in MATLAB. And then we'll tell it to print, say this, and then it'll print out exactly what we want, the cross of the two products, to 2 decimals, and in kilonewton meters. And as we see, the result is the same as what we want. So, as you can see, Python and MATLAB are pretty good at cross products. Position vectors. Position vectors are a lot more intuitive because it's really just a linear scale, just in 3 dimensions. And as you can see, the analytical formula is pretty straightforward. There's only 3 components. There's where you started, where you ended, and how far you went, right? So if you take where you started and you add how far you went, you get where you are right now. And if you take where you are right now and you subtract where you started, you get how far you went. And that's what we're doing just in 3 dimensions. And then the same thing applies where we'll subtract how far we went in our x, how far we went in our y, and how far we went in our z. We'll subtract all of those, and then we'll get basically the sum in Cartesian form of how far we went altogether. And for our problem, we have an elastic rubber band. It's attached to points A and B, as shown in the figure, as you can see right here. And we'll determine its length and its direction measured from A toward B. And in length, they mean magnitude. How far is the rubber band going? What length is it? And analytically, it's a pretty straightforward problem. What we do is we subtract B from A, or A from B, I'm sorry, and then we'll punch out this nice Cartesian, basically what area it's, or what length it's occupying in Cartesian form. And if we take the magnitude, which is we take all terms, square them, and take the square root of that, we get 7 meters. So the length of the rubber band is 7 meters analytically. Now, if we divide our position vector by our magnitude, we get a unit vector. And what that allows us to do is figure the angle from each axis to the rubber band. And as we see, it's 115, 73.4, and 31. Those are all correct answers. So the numerical approach in MATLAB gets a little fuzzier because it's just there's a lot of things we're going to do, but it works very similar to the cross product where we take x1, y1, z1, right, and we input those. Then we create an array. Then we create x2, y2, z2, and we create an array, right? And then all we have to do is subtract the two arrays, and we get the position vector, right, the variable position vector, and that gives us our Cartesian form array of the position vector. So that, -3, 6, and whatever it was, -3, 2, and 6, right? So keep an eye on that. So for the magnitude, all we have to do is use the norm command, and that'll do that square root of everything squared, and that'll give us the magnitude, and then we'll display that. And then for the angle, we're doing it sort of traditionally, which is to say pseudo-analytically. We'll just take the arc cosine, which is cosine inverse, of the angle in degrees will be equal to, the x angle will be equal to the arc cosine in degrees of the positive vector, right, position vector, of x over the magnitude, and then we do that for y and z, and that'll give us all of the angles from the coordinate axes in degrees. And as we can see, we get -3, 2, and 6, so we get the magnitude of 7 meters, and we get all of the same answers for our angles, and that means that it worked numerically. And for Python, it gets a little more complex just because there's a lot of funny stuff I did, but all we have to do is import math, so we're just going straight up arithmetic pretty much. And we're going to do a basic function. So we're going to tell it define the displacement function as variables a and b, right? And then our displacement is b minus a. And then all we're going to do is magnitude is, again, square root of all of our components squared. And then for components in displacement, right, we'll have our angle be equal to the math, a arc cosine, right, of our component over the magnitude for each component, right? And then we'll have that displayed from, for all of our components, we'll have that displayed to 2 decimal places. Displacement, yeah, round for displacement, everything's to 2 decimal places. And then we'll have it return displacement, magnitude, and angles. And then we'll have a list, components, position, x, y, z. So what that's doing is we're getting an input in terms of an array. So instead of just putting a equals 1, b equals 2, c equals 3, we're just doing a equals x, y, and z, and then b equals x, y, and z. So we're doing 3 inputs basically in one shot. And then obviously displacement, magnitude, angles equals displacement ab. That's pretty straightforward. And then we'll print all of our results. And as you can see, everything comes out as it should. All of our x, y, and z of point A, x, y, and z of point B, and it figures out -3, 2, and 6, which is correct, 7 is correct, 115.38, 73.4, and 31.0. And that is all correct, so that means that it worked. In summation, we can use cross products to determine perpendicularity, like we said earlier. You get an orthogonal vector, right, to your 2 vectors that you crossed. And then for position vectors, if you get a real formula for a position vector, then you can differentiate that take a derivative of it to create your velocity vector. The absolute value of your velocity is your speed, and then your derivative of your velocity is your acceleration. So you can use a lot You can do a lot with a basic position vector, as long as it has variables. If you have all constants in your position vector, that means your acceleration and your velocity automatically go to 0, as evidenced in Calc 1. Analytical methods are suitable, right? We solve these analytically, pretty straightforward. But imagine you had to do like 15 of these. It'd be a lot better just to have this program running, and you can knock it out. Can knock out all of them in a few minutes. It would not cost you a lot of time. And again, numerical methods will streamline, so they'll make your process more efficient and more streamlined. And both Python and MATLab are suitable for position and cross products, position vectors and cross products. As you saw, they were not terribly complex scripts. They ran extremely well, extremely reliable, and extremely robust. So overall, both Python and MATLab are suitable. So thank you for watching, and this is my project.